Yeah, clearly. I don't know why, but the thing doesn't go down far. Yeah. Okay, so topic here, parametric curves. All right. This is not calculus per se, and it's something that you probably haven't seen. We're going to do part of it now, and we'll do a little bit of it after we get into the vectors, because the stuff with straight lines is easiest done with vectors. So the deal on this is some people have some troubles at the beginning, but this is one of these tools that you're going to use later in the semester, and you have to just kind of crank them out. And there's some fairly standard examples that we look at. So the notion of a parametric curve is I can have a curve like y equals x squared. I pick something that's very trivial to graph. Okay, so that's sort of a parabola. And all you get is this picture. But if I tell you this is a path and somebody's walking along this path, I get nothing from this picture that indicates where they're starting, where they're stopping, or what direction they're moving in. So what a parametric curve does is to introduce a direction of movement along with the notion of time, where I am at various times. So I might write x is equal to t and y is equal to t squared. And this is a parameterization of this curve, and I'll show you several more. There's infinitely many different possibilities. Okay, so I want to observe that algebraically the square of x is what gives you y, and that's how I know it's a parameterization. We usually think of t as time. And so what I would observe is when t is 0, I'm at the point 0, 0. So I'm here at time 0. When t is 1, I'm at the point 1, 1. So I'm moving in this direction, and this would be the point 1, 1, and I would be here at time t equals 1. And similarly, when time is 2, we are at the point 2, 4, etc. And so my direction of motion looks like this. Notice that when time is -1, this is perfectly legitimate. I can think about time being in the past. I would be at -1, 1, but what I would see is that as time increases, my direction of motion here moves from left to right. Okay? All right, now, if I let x equal 2t and y equal 4t squared, this still gives me a parameterization of y equals x squared. So what's happening here is obviously at t equals 0, we're still at the origin. When t is equal to 1, using this parameterization, I'm at point 2, 4. So we're moving along this curve. We're moving from left to right. But what I'm seeing is that it's taken me t equals 2 in the first parameterization to get from the origin up to 2, 4. It's only taken me 1 unit of time in this second parameterization to get to this point, 2, 4. And so one of the things these parameterizations are going to give us, okay, is some sort of notion of velocity, also of speed, of acceleration. So this is kind of built in. As t increases, we're still moving from left to right. If I let x equal minus t and y equal the square of that, this is yet another parameterization of y equals x squared. But at time 1, we're now at the point negative 1, 1. At t equals 2, we're at minus 2, 4. And as time is increasing, we're moving in this direction. Okay? So, different parameterizations give us different speed of movement, velocity of movement, and also different directions. I can do this. Suppose I indicate that we'll just start this for t being bigger than or equal to 0. Now, you don't normally associate sine functions with a parabola, but notice that we still get that the square of x is y. And consequently, this still parameterizes that parabola. Well, what's going to happen here is at t equals 0, sine of 0 is 0. So we are starting at the origin. If we let time increase up till pi over 2, then sine of pi over 2 is 1. So x would be 1. Its square also 1. So we come up here to this point 1, 1, which we're at time pi over 2. But then as time goes from pi over 2 to pi, the sine function decreases back down to 0. And so we go this way, and we're going to be back at the origin when t is equal to pi. And then as time goes from pi to 3 pi over 2, the sine function becomes -1. It's square +1. So we come up in this way, and we are at this point at time 3 pi over 2, that point being -1, 1. And then when you go from 3 pi over 2 up to 2 pi, the sine function goes from -1 up to 0, and this will come back down. And as we continue on, it's going to go oscillating back and forth and back and forth and back and forth. Okay? So this does not parameterize all of y equals x squared. It just parameterizes this part to it. And the use of the sine function here is to cause the oscillation. The periodic nature of the sine function causes me to oscillate back and forth and back and forth. And you get typical restrictions on these functions. Sometimes you let x equal t, y equals t squared, and you might see 1 less than or equal to t, less than or equal to 4. So what this is going to do is start me out at the point 1, 1, and rotate me, I don't know, rotate is the right word. It's going to take me up to the point 4, 16. It's going to go in this direction. And I would be starting at that point 1, 1 at t equals 1. And I can end there at t equals 4. I could do this. This parameterizes the same curve as up above. You let t equal 2 when you plug in, you get the same exact formula, or you get the same exact point, 1, 1. You let t equal 5, and plug it in here, you're going to get the point 4, 16. So there's infinitely many of these parameterizations, and you know, even something like this, you can parameterize it in different ways. Okay? All right, so this is a general introduction to parameterizations. Typically, what down the line you're going to need to do is to provide parameterization of given curves. So there'll be some problems at the beginning where it asks you to sketch the parameterization. But ultimately, one thing we're going to really need is that you guys produce a parameterization. So let me work a little bit with that. parameterizations of functions. So this is going to be just like parameterizing y equals x squared. So if I said parameterize y equals e to the 3t squared, or excuse me, I guess I should make that an x squared. So y equals e to the 3x squared. Easiest way to do this with functions is to let x equal t, and then y equals the function. I mean, this is the easiest. Now, there's all kinds of other things you could do. You could let x equal 5t minus 2 and let y equals e to the 3 times 5t minus 2, the quantity squared. Why you would want to do this, I don't know, but you could. Keep in mind that if you were asked to parameterize this, let me see, from the point 1e cubed to the point 3e to the 27th, it's still along the function. As long as you let x equals t, y equals e to the 3t squared, the first coordinates of those points are going to be your beginning and ending place. So you just would go 1 less than or equal to t less than or equal to 3. These are really straightforward, no big deal here. Okay? Sometimes you want to affect the direction, but as in this problem, you can see that you can affect direction by putting minus signs in. Okay? All right.
Can you put that last page up for like 2 seconds?
Yeah.
So I can see it at the very bottom.
This guy.
Yeah.
Just the lower half here?
Yeah. It's just going to copy this down.
Yeah, that's fine.
Okay, I'm finished.
Okay, second thing, parameterizing circles and ellipses. We haven't really talked about ellipses, but I'll briefly go through them. But circles are pretty easy. If I want to parameterize this circle, so this circle has a radius of square root of 8. And what I really don't want to do is let x equal t and then solve this thing for y. The problem with that is your y here is going to involve a plus or a minus, and you have to be very careful there. The easiest way to do circles is to let x equal square root of 8 cosine of t, y square root of 8 sine of t. Okay. First of all, why is this going to give me a circle?
cosine's 1/2, sine's the other half.
Say again?
Cosine makes 1/2 and the sine makes the other half.
I'm not sure I know quite. It's not going to do that. It's not like this gives me half of the circle. It's these guys together.
Well, so cosine squared plus sine squared equals 1.
Yeah, it's your trig identity. Cosine squared plus sine squared is 1. What's the square root of 8 doing?
It's modifying the radius.
It's setting the radius. Look what happens if I take x squared plus y squared. What I would get is 8 cosine squared of t plus 8 sine squared of t. Factor out the 8, there's your cosine squared plus sine squared. 1, and so I end up with 8. Okay? Now, let's look at the circle. It's a circle of radius 8. At t equals 0, cosine of 0 is 1. Sine of 0 is 0. So at t equals 1, we're going to be here. Excuse me, at t equals 0. We're going to be at this point. Square root of 8, 0. Okay? Now, my question is going to be clockwise or counterclockwise?
Would be
Counterclockwise.
Counterclockwise. Okay. The easiest way I know of to think of this is if I know where I'm at when t is 0, when t starts increasing, both cosine and sine are positive. So cosine and sine start off positive. And that means I'm going to be moving into this quadrant, into quadrant 1. So my orientation is going to look like this. Okay? If I look at x equals minus 5 cosine of t and y equals 5 sine of t, at t equals 0, well, cosine of 0 is 1, so I'm at the point minus 5, sine of 0 is 0, so I'm there. In this case, I have a circle of radius 5. I'm starting out here. As t becomes a little bit positive, cosine is positive and sine is positive. So that means x is going to start off negative and y is going to start off positive. So as t becomes a bit positive, cosine of t is positive, sine of t is positive. And so because of this minus sign sitting up here, we get negative x. Well, it better be if we're starting over here, because I don't care what direction you go, x has to be negative. But y is positive, that means my orientation is like that. You're going to be back at this starting place when t is 2 pi. Sine and cosine are both periodic. Period is 2 pi. Now, in terms of units of time, it's hard to talk about 2 pi minutes or 2 pi hours. So more typically, you might see something like x equals minus 5 cosine of 2 pi t, and y is 5 sine of 2 pi t. And this is going to give you the periodic behavior, it's going to give you the circle behavior, but it's going to do one revolution at time 1. So my period for both of these functions is 1. And that means I do 1 full revolution in 1 time unit. So I can speed up or slow down my motion around the circle by messing with the period of my function. All right? Okay. When you mess with ellipses, let me see. This is stuff we'll have to talk about in more detail. Okay. These are both equations of okay, look at the first guy. It's the equation of a circle. And if I say they're both equations of, then they are the same. Okay? They're both equations of circles. How do you identify them as such? You guys know? This is the analytic geometry. These are the conic sections that they'll briefly talk about in chapter 11.
Squared sections are identical. Squared sections are identical.
Yeah, we've got coefficients of the squared sections both being the same, meaning also the same sign. There are linear terms in the second example. That's okay, but what you don't have are any cross terms, x, y terms. Okay? You have an x squared term and a y squared term. And their coefficients have the same sign and the same exact value. Now, completing the square would give the center of this circle. I'm not going to worry about that. When we work with circles, they'll be centered at the origin. But keep in mind that you have to divide out that 3 to say that the radius of this circle is square root of 8 over 3. Okay? But what makes these circles are the presence of both an x squared and a y squared, both of the same sign with identical coefficients. If I write this, or these are algebraic representations of ellipses. So ellipses look like this, sort of, or depending on which way they're squished, like this. And they have two, what they call foci, plural, focus. I can't remember if they put one eye or two in. But they've got two of them, and you can easily make an ellipse if you put something like a looped string and 2 points pinned down and loop the string around it and then kind of pull the string out to the edge and rotate it around. You can get equations of the ellipse. Well, these are the equations. You can put them in the form where you can find these coordinates. You can figure out, is it longer in the horizontal or in the vertical sense, is all of this. Here's what I'm primarily interested in. This guy has got linear terms. It's going to move that ellipse so that the center is away from the origin. Completing the square would tell you where that point would be. So be it. If we're working away from the origin, you could just translate everything back so that it's centered at the origin. So that we'll primarily work with the ellipses that are centered at the origin, if not primarily, exclusively likely. Algebraically, what distinguishes this from a circle is when on the same side of the equal sign, these coefficients are not identical, but they are both positive. If, on the other hand, I had something like x squared minus 2y squared equals 8, I would get something that, we'll discuss this a little bit later, it's a hyperbola. Okay, which, depending on which of these in magnitude has the bigger coefficient, will either be this or this. These are not parabolas, although they will have that same kind of shape. But technically, parabolas come from, okay, this is not the first time I'm going to do this. So, let me see. This is what happens when I accidentally hit the power button. Yeah. Okay. In any case, ellipses, to my way of thinking, are basically circles. They don't really behave that much differently. If I was going to parameterize this, I'm going to have x be cosine or sine and y be the other trig function with the appropriate number in front to rig the radius. Okay? And depending on where you put the cosine, where you put the sine, and whether or not you've got negatives and where the negatives are, You can start your circle at a variety of places and have the rotation go clockwise or counterclockwise. Ellipses are going to basically be parametrized in the same way. So if I went to parameterize x squared plus 2y squared equals 8, then I'm going to begin with x equals, say, cosine of t, and y equals a sine of t. Now, this gives me a circle, but it's a circle of radius 1. I want an ellipse. So what I want is to exploit the fact that x squared plus y squared is 1. So if I put x equals cosine in, I get the cosine squared, but too much of this y squared. So I have to rig it so that I get the same coefficient in front of the cosine squared as the sine squared. So what? If I put the square root of 2 in, then this would give me x squared plus y squared equals 2 cosine squared, excuse me, 2 here. I'm plugging into this equation. So this would give me 2 cosine squared of t plus this 2 sine squared of t. And then I can factor out my 2 and get cosine squared plus sine squared, which is 1. So this will let me add it up to 2. But I want it to add up to 8, not to 2. So therefore, how do I get it to be an 8? Where? Okay, so if I put square root of 8 in here and square root of 8 in here, you take a look at x squared plus 2y squared. What I'm going to get is 16 cosine squared of t plus 2 times 8, so another 16 sine squared of t. That's going to be 16. So that's not going to do it. The problem here is that this square root of 2 is interacting with that 8. So
Square root of 4.
x equals, well, square root of 4 is 2. X squared plus 2y squared. Do we want it here? Take a look. Okay, so x squared is going to be 8 cosine squared of t plus, okay, plug in, 2 times y squared, that's going to give you, not going to give you the 8. In fact, I think I fouled up when I plugged in here. Oh, it's hard to see. Never mind, I didn't foul up above. So this right here was from when I let x equal square root of 2 cosine of t. Y is simply sine of t. So this square root of 2's got to go. Do you see what I'm saying? So now, when I put in y squared, what I'm going to get is, oops, 4 sine squared of t, and that's not good. So what do I do?
Could you just do square root of 2 on both of them?
Yeah,
Cosine.
I mean, the way in which I would think about this is, yeah, sticking your square root of, I don't know, would square root of 2 do? Because then you square it, yeah, that would work here. I shouldn't be putting in the same stuff out front though. Two y squared. Oh no, this isn't it. This is fine. I'm sorry. This is 2 times the square of 2 sine of t. So that works. Okay. So this is going to do it. Okay. Let me make a couple comments about this. I can sit here and fiddle around and come up with a nice little formula for when we're messing around with ellipses. The best thing I know of, the best skill to take with you is the skill of fiddling until you get it right. So you have a general idea. It should be pretty clear from the circles what you're going to do, and the rest of it is adjusting. So you try something and then go from there. Adjust until you get it actually popping out, okay? All right? Now, in actual fact, most of the time, we'll be looking at circles. So, occasionally we may have an ellipse. All right? Questions on this? Okay, the third thing that is commonly used as examples, parameterizations of lines. If not a line, then a line segment. Okay. This is going to wait until we're in chapter 12. So the book will go through this.